My name's Daniel Cartwright. I am going to talk to you about state machine testing with Hedgehog. It's a continuation of my talk from last month, testing purely functional programs with Hedgehog. So I want to give a recap of what the last talk was about. So the whole idea behind Hedgehog and property testing is that instead of coming up with unit tests where you come up with the inputs yourself and they're hard-coded, your inputs are generative, so your tests are parametric in the input. This ends up tackling the coverage problem a lot more. It does a better job of getting more coverage. So, and in Hedgehog, it's very easy to write tests for pure functional code to make sure that they're correct. You just write out your generators. You declaratively describe what the properties of your code are supposed to be, and then Hedgehog will figure out the rest and show you pretty counterexamples if you're wrong. And that was the gist of the talk. The problem is that a lot of real world code is not purely functional. It's not pure. So you have a lot of I/O, you have a lot of concurrency, you have a lot of sort of mutable state, and it's really hard to get around that. That's just how complicated real world programs work. So most of the time, once people get around to that part, they sort of either do a really bunch of unsafe hacks in QuickCheck or Hedgehog to not, at least in Haskell, to end up not accomplishing much, or they write a lot of code and they don't get to test the whole time because it's supposed to be for testing pure code, or they end up writing unit tests anyway and just have like an impure test suite that just maybe it assumes it can do some kind of connection to a real database. Then you get into doing mocking and all sorts of stuff, but then you're not real. You have to put a lot of work into mimicking the actual state of your system, which can be tedious. Which brings me to today's talk, the majority of which is going to be about using Hedgehog to do state machine testing. And I'll get into what state machine testing is. The talk will be given in Haskell. Just know that there are ports of Hedgehog to other languages, and whether or not it's as easy to express the Hedgehog machinery for state machine testing in any other given language, it depends, but it's not solely dependent on Haskell. You can do this in other languages, which, as evidenced by the fact that, for example, Hedgehog itself has ports to many other languages, such as Scala, F#, and R, in addition to its first of Haskell. So, these techniques are applicable in other languages, and in fact, I am going to show you an example of a translation from Erlang to Haskell, where we take some registry that operates concurrently and see if it's actually thread safe using a Haskell Hedgehog. So I'm gonna open up some code now, and first I want to go over what a state machine is. I tried to download this image from this blog post, but whenever I do that, it looks like this, which it does not have a lot of the things that were in the image. So for anyone who doesn't know how to read state machine diagrams, this is a really simple state machine that encodes how sort of turnstiles work. If you've ever been to a subway or public transit system, you've encountered some form of a turnstile. So the way to read these is that you have states and transitions between those states. This this black dot here points to our initial state, and then the lines, the orbs are, these circles are our states, and the lines are transitions between our states. So our initial state is locked, and if we follow this arrow, we insert a coin, becomes unlocked, we push it, and then the unlocked turnstile becomes locked. And if we take a locked turnstile and we push it, it takes it back to being locked. Because if the turnstile is locked, you can't push it again to unlock it. You have to insert a coin. And then if the turnstile is unlocked, inserting a coin does nothing, and you don't get a refund. So we're actually going to encode this in Haskell, and we're going to write some tests to see if it actually, if it actually holds up to certain requirements. So the first thing to do is come up with our state, and this is just a simple sum type. We have a turnstile state, and it can be either locked or unlocked, which if you look back at the diagram, those are our two states. Now, we could do something simple like have, encode this in a very functional way, in a very clean way, which is to have a function, sort of like this, like transition, where, turnstile state to turnstile state, and then we could do, transition locked equals unlocked, and transition unlocked equals locked, and then just have some like really easy pure invariance. However, that's not the talk we're giving today. We're talking about having a turnstile server, which people from all over the world are connecting to, and you want to make sure that your turnstile behaves properly with your millions of clients connecting to some obscure turnstile web server for whatever sick fun they're having. So in Haskell, there's a few places where you can have sort of mutability, where you can have mutable references, and one of those is an IOREF. So an IOREF is a very simple mutable reference to some value that you can mutate inside of the IO moment, which indicates for the type system that mutating it is impure. So we have this turnstile, we have this IO, so our turnstile is not just modeled by some turnstile state, it's an IOREF of turnstile state. Then we can create a new turnstile, and our initial state is locked, so it's important that when we create a new turnstile that it's locked. And now we're going to, so now that we've encoded our states, we need to talk about our transitions, and a very useful function for talking about, for mutating IOREFs in an atomic way is atomic modify IOREF. And so this is a way to modify IOREF safely in a multi-threaded program. The idea is you just have an IOREF with an A inside of it, and you have a function that takes an A and returns an A and a B. And what it will do is it will mutate the IOREF with this new A value, so it's sort of a state transition, and then give you the B value inside of the IO monad. That's all it does. Does everybody understand that? Okay. So, for example, in order to insert a coin, when we insert a coin, we need to update our state. So we take our IOREF with the turnstile state, and we modify it to return to update the state to unlocked. So and we don't actually have to care about whatever the input state is here, because no matter what, inserting a coin will keep the turnstile unlocked. Because if the turnstile is locked, it will unlock it, and if it's unlocked, it will stay unlocked. Then we have, push turnstile, which does the same thing, but it will return, and the value that we're returning is a spool, which represents whether or not it is, whether or not it's actually locked. So false, it's locked, and unlocked means it's, yeah. So when we modify this IORef, we have to case on it. So when it's locked, if we're pushing the turnstile and it's locked, we should not be able to get into it because it's locked, you haven't inserted a coin yet. And if it's unlocked, then pushing it will lock it, right? So you're going through the turnstile. And this is our initial state, T-locked. So our initial state, in our initial state, the turnstile is locked. Now we're getting into where Hedgehog state machine testing requires some sort of weirdness at the type level, but for the most part it's non-invasive. You usually don't have to work with it at all, you just have to provide these. Your state has to be parameterized by some functor, and internally Hedgehog will instantiate this type variable with whatever functor it so pleases. There are two of them, and be able to sort of imbue different behavior based on which functor it is. But for our purposes, you don't really need to worry about that. You just need to know that your state is parameterized by some functor, and you have these, you have two states here for your model. You have locked and unlocked, and you have an initial state. So now we're also going to talk about our transitions, and we're not going to talk about our, actually, yeah, we are. So we only have two transitions. If you go back to this diagram, you can only push or insert a coin. Even though there are multiple arrows, every single one of them is either pushing or inserting a coin. So your transitions also must be parameterized by the same functor. Note this, that doesn't matter. You just have, there's just a data type indicating which transition we're doing. And you can ignore this H-traversable instance. That's also another implementation detail that you just have to deal with. But again, not too invasive. So now we're actually going to write some tests. We have, so to recap so far, we've encoded what our states are. We can start with an initial state, we can insert a coin, and we can push a coin. So we have our states and our transitions. Those are the three things that make up a state machine. Initial state, states, transitions between those states. This test, it takes a turnstile, and let me explain what this command stuff is. So you may see this command type here, and it's parameterized by n and m, which you just, you don't really need to worry about, but this model state is important. So the idea is that you need a way to generate a state. So you need a generator for some state to start out with, and then you need an execution function, which actually executes that state, and then you have a list of transitions, and these transitions encode preconditions. So what conditions must I satisfy before this transition has occurred? Conditions, and also conditions like after the transition has occurred. So you have preconditions and postconditions. For this one, our generator is supposed to take our state, and it returns a maybe value. And if it returns nothing, that means it failed. And if it returns maybe of something, that means we actually were able to generate a new state. So we can always insert a coin, right? So we don't need to see the state. It doesn't matter what state we're in, we can always do that. And then executing a coin, you know, if we insert, that's just inserting a coin, right? Okay. So then here, you know, after our coin action, after we insert a coin, the turnstile should be unlocked. That's what this is saying. You know, update, then we take our state and whatever this is, and then we say that this is unlocked. And then our ensure, which, you know, ensures that we have like certain preconditions and postconditions. We don't really care about the preconditions again, because inserting the coin, you can do any time. So after, but we say after, you know, after inserting the coin, it must be unlocked, right? Then this is, I'm not going to go through line by line what every single thing means. The first one was just to sort of get you used to what was going on. So this one, you know, this is actually testing that after we push, you know, it's locked. If you push the turnstile, it should lock immediately afterward. And then, yeah. So there are a few different conditions here to uphold. And then this one is also, if you push it and it's unlocked, then it should lock afterward. There's just a bunch of stuff that you can test. So now here's how you actually run those tests. So if you look at the test function, I talked about this in my last talk. There's Hedgehog has check sequential and check parallel with this template Haskell splice discover, which you can think of as like a meta. Template Haskell's meta programming. So what discover does is it goes and finds every single function that begins with prop underscore, and like turns that into a test that it's going to run. Like it generates the testing code for you. So I have two versions of the test here. This one is very simple. We create a new turnstile, and then what we do with we generate a list of actions using Hedgehog's gen sequential. So if we go over here, gen sequential, yeah. So we generate a sequence of actions from an initial state and a set of commands. So you give it a set of commands, and it will just generate random sequences of those, starting from your initial state, and then it will run those sequences to make sure that, you know, no invariants are not upheld. So here we've got gen sequential, and this range encodes like the number of actions to actually perform. And then we've got our initial state, and then we've got, you know, all of the properties that we just talked about here. So, and then we execute sequential with our initial state and our list of actions. So, what we can actually interpret prop turnstile meaning is that we start out with a new turnstile, we create a bunch of, random actions, random transitions, and that at any point in time, our transitions, you know, should not break the invariance of the system. And then the second example is basically the same thing, but you'll notice that it is parallel. So you can imagine that this system, when running all of these actions in parallel, might encounter some problems. As is the case with a lot of real world code. So I'm going to comment that out real quick, just so we see. And in this lower left-hand side, you'll see state machine.test. You'll see the actual output of this. So it passed 100 tests. So everything worked out completely fine. That's awesome. But what if we change our initial state? So the fact that it passed those tests means that Hedgehog is pretty confident that, you know, it didn't uncover any problems. you know, like all of our assertions and assumptions about the system were correct. But let's change this to unlocked. What is that? What happens there? So we'll reload that, and then it fails immediately. So it fails on S push unlocked. So here, we're saying that after we push it, yeah. So before we push it, so if we gain admission, the turnstile gate should be locked after we get in, and that's what that Boolean value is. If you recall that like push turnstile returns as bool. So assert, requires that thing needs to be true. So our post condition is false because all of a sudden, the initial state is where the gate is unlocked. So this will return false because the gate is locked after you push it. So if it starts out unlocked and then you push it, right, it will lock, and then, okay, you got it?
So, everyone? Meaning that on the next test, we've set two things. I mean, we've set initial state to unlocked, and then we run push, and then it changes it to lock. So the next test is going to say, whoa, hold on. Okay.
So after every transaction, after every transition, your invariance and assumptions about the system should be upheld, and that's what Hedgehog is testing. And if you notice, it failed after one test.
After one test.
It found it on the first try.
Right, but the first try was.
This isn't a really easy one to find on the first try, but.
But I mean, it didn't fail because it was unlocked at the beginning. It failed because after it got pushed, it was locked, but we had set the initial state. So then for the next time, our state machine is now locked, but our invariant is, hey, the initial state should be unlocked. Is that correct, or am I misunderstanding this?
I think this is another moment where I'm getting confused by words, but.
Okay, so we went back into the code and changed the initial state to unlocked, right?
Yeah, so we changed it to unlocked.
So then our test, we've explicitly stated that okay, the initial state is unlocked, and then we run push unlocked on it, which then
so if we look at
changes the state to locked, right?
If we look at S push unlocked, what this says, if we're trying to push on here, let's look at our graph again. If we try to push on something that's unlocked, it should become locked again.
So then the next iteration through, is that an after?
Yeah. So our after assumption is that like the turnstile gate should be locked, but we left it as unlocked. So before we have it as unlocked, and then this Boolean is false in this case, because if we push turnstile, that means we got, if it was locked and then it locked, we got false. So that means as soon as we push it, it becomes locked, and then if we try to push it again,
right,
then it's locked. Okay.
I have another little question. Since this is such a simple example, there's really only like 4 things to test, right? What are you going to try to do, and what state is it in already?
Yeah.
Right. So in that case, does Hedgehog go like, you don't need 100 tests? We completely exhaust it after 4.
No.
Okay.
No, it's it will try to do like coverage, and there's even stuff in Hedgehog to test how much of the state space that you're actually getting coverage of.
Okay.
So you can reliably estimate how much coverage you're actually getting.
Right.
Because it's generative, and the state space of a lot of these things is so large, then you can't get then you can't get 100% coverage. So, yeah. So, oh, yeah, so like, the basic idea is that we tried to push it thinking it was unlocked, but it wasn't.
Oh.
In the thing that we were just talking about.
Right, but on the first iteration, we've explicitly, the initial state we set to unlocked, and then we pushed it and not reset it to locked, or moved the state to locked, right? So when the next pass through, we try to push and it's locked.
Yeah, and it's locked,
Right.
but we thought it was gonna be unlocked.
Right, okay.
So
let's see
if I undo that, fix our initial state. Now, I'm gonna show off the parallel testing. So if I reload, so this is gonna run 2 tests now because we have the sequential test and the parallel test. And the parallel test here, you can actually see is basically the same thing, except it's going to see if all of these things in parallel make sense, which they're not going to. This is not, you know. So it can show you that it failed. So, yeah, it says, and Hedgehog will say like no valid interleaving, which means it could not discover a, you know, a set of parallel transitions to run in parallel in which the invariance would be upheld at any given point in time, which is, you know, pretty useful. Does anybody have any questions? Because I'm about to go into a more complicated example. Any questions? Okay. So, this example I did not write. This is actually, this was written by Jacob Stanley, and it's actually a translation of some Erlang code. This is Erlang code for a process registry. So the idea is that you want to register processes, and you want to register, unregister, and I meant to do that. So yeah, you want to create a process. You also want to register processes, and you want to unregister processes, right? So really simple. Like it's one of the simplest possible, you know, process registries that you could think of. This takes the same ideas and actually encodes it using the Hedgehog state machine stuff to test whether or not you can actually run something like this and you won't run into bugs. And again, it's a direct translation of the Erlang code, which you can find here. Yeah, so we have process IDs, process names. We have some state, which is a set of process IDs, and then we have what is registered, which is a dictionary, a map from names to process IDs. And then in our initial state, everything is empty, like we have no processes. And then this is our first transition. We want to spawn things. So we need to spawn a process, which means it needs a process ID and a name. Yeah, so if we look at IO spawn, this it creates a new process ID, and then it will increment the global process ID counter and give us the process ID that it got, right? And then on an update, we want to, like on each transition, we want to insert the new process that we created into our state, right? So we want to add to the registry that process ID. Then we want to register process IDs. I'm not gonna continue boring you guys with the logic because I'm sure you could think through it. It's not complicated. The whole idea is just you spawn, register, and deregister things. And then this is a fake process registry, it's just a hash table from string to int, and string is the name, int is the process ID. We have like a proc table and stuff. Then we can run two tests. We have the prop registry sequential and prop registry parallel. This is an example, in a turnstile application, we really only would have, one turnstile per user, so to speak. So testing whether or not a turnstile behaves properly, a turnstile state machine behaves properly under 15 people trying to go through it at the same time doesn't really make sense. But a process registry application, for example, you definitely want that to be able to run, things to execute in parallel, because in real machines, real systems, processes spawn, at the same time all the time, and you don't want bugs. So this one, since it's using Discover, I'm going to actually comment this out, and we're going to run the prop registry sequential state machine par.tests. So that succeeded. That's totally fine. So running every command it could think of, and those commands are, again, it will generate sequences of spawn, register, and unregister, and make sure that at any given point all of our assumptions and assertions about the system will be upheld. But let's add in the parallel case. That failed. So you'll see, okay, user error, IO register already registered. So what this is saying is that Hedgehog was able to come up with a sequence of actions, a sequence of transitions to our state machine that, well, I guess when run in parallel, you could actually register a process that you already registered. And I think that's pretty cool. It's actually not that invasive to the code. You could argue that to existing code it could be a little invasive, and I would agree with you. But there's been some really interesting work. God, what is this guy's name? Wickstrom Hedgehog. Yes. So this guy's name is Oscar Wickstrom, and he works on something called composition, which is a video editor written in Haskell. And he wrote it for his use cases, but it's a general purpose video editor, but he made it so that it streamlined certain things. And what those things are, I don't know. I suck at editing video. But he actually uses Hedgehog extensively, including the state machine testing, to actually test and find bugs in this application. And it's not a small application, it's large. It supports what most modern video editing softwares do. This is just slides. I guess he was talking over this. Let's see. I don't care about inline Java testing. Well, actually, that's sort of cool. But yeah, there's a composition. It's a video editor tool built for screencasting, and it looks nice. And I don't know. Let's see. Wickstrom Hedgehog composition. I know he's got blog posts about this. just went to. Property-based testing in a screencast editor. So you could imagine in a screencast editor where you're dealing with like GTK or whatever, there's probably a lot of mutable state going on, a lot of, a very, stateful code, a lot of stuff that you may want to test because it's very I/O bound, very real world bound. So he actually has some blog posts where he talks about property testing and, also state machine testing for this, and he has actual case studies that you can walk through, and there's a lot of cool stuff coming out of this, because I think it's probably the largest project that actually uses Hedgehog state machine testing at this scale. That's the gist of my talk. It was mostly example driven and sort of just talking about the ideas, and I didn't want to talk about the implementation too much because that would just bog you down in a lot of details that are not pertinent to actually using it. So, does anybody have any questions?
I have one. You stated that Hedgehog can at least describe or give some guess or measurement of how much of the state space it's covered with its specified number of tests. Can you show me that? Where that feedback is?
I have actually, admittedly, I've never used that, but I know it can do it. There's like a S.
Does it like do some kind of static analysis or something, or?
No, it does. What it will do, it will sort of like install a listener on as you're generating things and running tests, and it will try to sample a bunch of stuff and estimate how much of your coverage you're actually getting, which is really useful because you can run that, and if Hedgehog is like you're getting like 10% coverage, you're like, well, that's not good. So like coverage success, coverage failures, it's basically right here. Hedgehog Haskell coverage. I think someone's written a blog post on this. I don't know where it is. I'd have to ask, but yeah, that's like a really useful thing for generative testing, because it's like in most inputs you cannot tell how much you're actually covering. So, and I know they put a lot of work into making sure it's statistically accurate too. So, and this is the Erlang code. My Erlang is admittedly extremely rusty, but I mean, it should be like relatively, based on what I said, this should be straightforward. So, does anybody have any further questions? Any questions? Are there any questions that came in from online?
Nope, we don't have any questions online either.
Okay.
You must have just done a great job of explaining it.
I do not feel like it, but okay. Well, thank you, and that's all.